We will pick up from capillary so we can look at how things cross the capillary wall. So we see here in this figure, this is showing a capillary, the lumen, and this is showing the walls with the intracellular clefts and fenestrations. And so we can see different ways that things will cross the wall. The first is diffusion, and this means that things go down their concentration gradient through passive transport, diffusion, and osmosis through things like intracellular clefts or fenestrations, depending on the type of capillary that it is. Notice that we see over here transcytosis, which is where the cell makes vesicles to take things either into the cell, endocytosis, or out of the cell, and exocytosis, whenever it can't go through an intracellular cleft or fenestration. But what we're going to look at mostly is kind of a take on osmosis and diffusion called bulk flow. And in bulk flow, that means we are going to move large amounts of things through the cell. So we see diffusion is moving down a concentration gradient with simple diffusion. Some certain things are able to move by diffusion, like oxygen, CO2, some hormones. Transcytosis, this happens in large lipid-insoluble molecules that cannot cross by diffusion. And then bulk flow, the definition is a passive process where large numbers of ions, molecules, or particles move together in the same direction. So we're going to see moving in bulk either into a capillary bed or out of it. And it follows diffusion, where it goes from an area of high pressure to an area of low pressure. So keep that in mind as we walk through bulk flow. It's going to go where the pressure is high to where the pressure is low. Now we've got two types of pressures to consider when we consider this moving from high to low pressure in bulk flow. The first is osmotic pressure, and osmotic pressure is, in my words, the tendency of a solution to draw water. So if something has a high solute concentration, a higher solute concentration than another side of a capillary, then that is said to have more osmotic pressure, because osmosis will follow toward that higher solute. It is the tendency of a solution to draw water. So another definition, it is the force we must apply to prevent water from moving into it by osmosis. So if something has a higher osmolarity or higher solute concentration, it has a higher solute concentration. So notice on the figure on the right, solution A has higher amounts of solutes, which are the purple molecules. So solution A has the higher osmotic pressure when compared to the blue side with less purple molecules that has a lower solute concentration. The other is the hydrostatic pressure, and the definition of hydrostatic pressure is just the pressure that a fluid exerts on the walls of its container. So if we look at hydrostatic pressure, that means that if you think about the blood pressure inside of your vessels now, that's what we're measuring when we measure arterial blood pressure, just the pressure the blood has on the sides of its container. Its container are your arteries. So hydrostatic pressure is inside of those vessels. And of course, you could also have some hydrostatic pressure of the interstitial fluid pressing back on the capillary bed, although that should be quite low. So you're going to see some fairly constant numbers when we look across the capillary bed, but hydrostatic pressure is going to be the things that changes most. It changes from where it enters the capillary at the arterial end to where it goes back to the capillary at the venual end. So remember, blood is going to flow from arteries to arterioles to capillaries back to venules and veins. So the arterial end of the capillary, where the arteriole flows into the capillary, is going to have a higher hydrostatic pressure than where the capillary and venule meet to go back. So this hydrostatic pressure gradient helps to drive water out of the capillary at the arterial end and fluids back in at the venual end. So we will observe this. So notice the point over here in red, this is showing a systemic arteriole, and over here at the right side of the screen in blue, this is a systemic venule. So we see water, H2O here, going out of the capillary bed at the arterial end of the capillary, and it's coming back in at the venual end. This is what should happen, and this is based on the changes of hydrostatic pressure. We're going to make this make a little more sense. It'll look a little bit more complex, but really we're making it make a little bit more sense with the equation that we see at the bottom. So if you're taking notes, you may want to write this down. NFP stands for net filtration pressure. So to find the net filtration pressure, you first take the BHP, the blood hydrostatic pressure, plus the IFOP, which stands for the interstitial fluid osmotic pressure. Let's look at this figure and I will point out where blood hydrostatic pressure and interstitial fluid osmotic pressure is. Blood is confined inside the arteriole, capillary, and the venule. Interstitial fluid, remember, is what is surrounding the tissue cells out here, so it's in the blue. So blood hydrostatic pressure is the pressure that a fluid exerts on the walls of its container. So it's going to be the blood pushing out on the ends of the capillary. Interstitial fluid osmotic pressure means that interstitial fluid is drawing water out of this capillary due to dissolved solute. So that's the pressure that interstitial fluid is pulling water out of this capillary. Now I'm pointing here at one end, but notice that blood hydrostatic pressure is located anywhere along the inside of the vessels in this figure. Interstitial fluid osmotic pressure is anywhere in the blue in this figure. Both of these, blood hydrostatic pressure and interstitial fluid osmotic pressure, notice, promote the flow of fluid out. So blood hydrostatic pressure is pushing out on the walls of the container. Interstitial fluid osmotic pressure is pulling fluids out of the capillary. So whenever we're talking about fluids coming out of the capillary in bulk flow, we consider that filtration. So you can make note, blood hydrostatic pressure and interstitial fluid osmotic pressure are filtration pressures. We're going to take the filtration pressures minus these two, BCOP and IFHP. These are both what we call reabsorptive pressures. Reabsorptive means that it goes back in. Notice this is what's primarily happening at the venule end. It's drawing fluids back into the capillary. BCOP stands for blood colloid osmotic pressure. Blood colloid simply means the large plasma proteins confined to the blood. So that is inside of the capillary. So blood colloid osmotic pressure means that the presence of plasma proteins inside of this vessel is going to draw water back into the capillary. Interstitial fluid hydrostatic pressure is what IFHP stands for, interstitial fluid hydrostatic pressure. This is the pressure that interstitial fluid will exert on the walls of the capillary. For our purposes, that is generally going to be 0. So we can conclude at this point that's going to be 0. So it's the filtration pressures minus the reabsorptive pressures. So filtration is a pressure-driven movement that pushes things from blood capillaries into interstitial fluid. That's your blood hydrostatic pressure and your interstitial fluid osmotic pressure, like you see here at the first part of the equation. Reabsorption is the movement of fluid and solutes from the interstitial fluid back into the capillary. So those reabsorptive pressures are what you see after the minus sign here, blood colloid osmotic pressure and interstitial fluid hydrostatic pressure. Under normal conditions, what we will see, going back here, is that when we put in numbers at the arterial end, we usually see filtration out of the capillary, and at the venule end, we usually see reabsorption back into the capillary. On average, most all of that interstitial fluid, that bulk flow that comes out at the arterial end, is going to be reabsorbed at the venule end. That's about 85% that is reabsorbed. Now that the rest of that becomes lymph and it enters this lymphatic capillary and returns to the cardiovascular system from there. If filtration greatly exceeds reabsorption, edema occurs. Again, this is what happens if we do not reabsorb enough back into the venule end of the capillary. So we had talked about cirrhosis of the liver before, and this is where the liver might fail to make proteins, a lot of those big plasma proteins that are responsible for blood colloid osmotic pressure. If you get a positive number, which is what should happen at the arterial end of the capillary here, then the filtration should override reabsorption and you get movement out. At the venule end, you should get a negative number. Notice here they got -7. So negative would mean that you were pulling fluid back into the capillary. So plugging in numbers here, notice overall net filtration pressure. If they put in 13 minus 7, you get 6. A positive number would mean we're forcing fluid out. Here, you putting all those numbers in on the venial end. 15 minus 22 is -7. That would mean that it's drawing fluid back in here at the venial end. And you'll have some examples to do and plug those numbers in and see how this works. Kwashiorkor, this is a condition. This is not cirrhosis, but this is related in the same family. If you've seen children that are starving that have the muscle wasting, where the body is breaking down proteins in muscle and metabolism, so they have the very thin limbs, but you'll notice they have the very swollen bellies sometimes. This is the same type of thing that we get with ascites with people with cirrhosis of the liver, because the body is starving and it might fail to have the amino acids to make those large plasma proteins that give us blood colloid osmotic pressure. If you don't have blood colloid osmotic pressure, you cannot reabsorb fluid at the venial end. So you've got this fluid that builds up and makes the bellies larger. So that is a kwashiorkor. That is what causes that condition in severely starved people.